All right, think about this. How hot is hot, and how cold is cold? I mean, we feel temperature every single day, right? But how do you actually measure something that you can only, well, feel? Turns out the secret isn't to measure the heat directly. Nope. It's all about watching the predictable, visible effects it has on the world around us. So let's dive in and see how we cracked that code. Okay, so here's the game plan. We're going to start with that big problem. How do you measure a feeling? Then we'll get into the physics of expansion, find some universal rules using what are called fixed points, take apart the classic thermometer to see how it works, and wrap things up by looking at how electricity gives us a totally different way to measure heat. So let's start with that core challenge. Our sense of touch is, well, it's not very reliable, is it? What feels warm to me might feel kind of cool to you. And for science, that's a big problem. We need something objective, something repeatable. And that brings us to the big question. How can you possibly put a number on something you can't even hold in your hand? Well, the solution was absolutely brilliant. It was to just stop trying to measure the heat itself. Instead, scientists decided to measure something else that changes in a really predictable way because of the heat. And that predictable change, well, that's where the physics comes into play. See, scientists figured out they could use a reliable physical effect as a sort of stand-in, a proxy for temperature. And the most common one, the one we all know, it's thermal expansion. It's a really simple idea when you get down to it. When you heat most things up, their atoms and molecules get all energized and start bouncing around, pushing each other farther apart. It's kind of like a crowd of people starting to dance. They take up more space, so the substance expands. And when you cool it down, they huddle back together and it contracts. This super predictable change in volume, that's the secret sauce for building a thermometer. But, expansion isn't the only game in town. There are other things that change predictably with heat, too. For instance, the electrical resistance of a material changes. We're going to put a pin in that idea for just a little bit, though, because for now, we're sticking with expansion. Okay, so it's great that we have something that expands and contracts with heat. But think about it, a line of liquid going up and down in a glass tube is pretty useless without a scale next to it. To create a scale that everyone in the world can agree on, we need some universal, super reliable landmarks. We need what are called fixed points. So what's a fixed point? It's just a temperature where something really obvious and repeatable happens. The perfect examples are the melting point of ice and the boiling point of pure water. No matter where you are on Earth, assuming standard pressure, these things happen at the exact same temperature, every single time. That makes them the perfect anchors for building a reliable scale. And the two most famous fixed points are, of course, the ones that anchor the Celsius scale. We take the temperature of melting ice and we say, okay, that's our 0. That's the lower fixed point. Then we take the temperature of pure boiling water and we say, all right, that's 100. That's our upper fixed point. And bam, with just those two universal constants, we've got the foundation for a scale we can all trust. So how do you actually use this to make a thermometer? It's beautifully simple. You take your unmarked glass tube with the liquid inside, you stick it in a bath of melting ice, and you make a little scratch where the liquid settles. That's your 0. Then you move it over to a pot of boiling water, and you make another scratch where the liquid rises too. That's your 100. And then you just divide the space between those two marks into 100 equal little lines. And just like that, you've got yourself a calibrated thermometer. All right, so let's put all these ideas together. Thermal expansion, fixed points, a calibrated scale, and look at the tool we all recognize, the classic liquid and glass thermometer. The design here is so simple, but it's totally genius. You've got this big reservoir of liquid sitting in the bulb at the bottom. Now, when that large volume of liquid heats up and expands just a tiny, tiny bit, it has nowhere else to go. It's forced up into that super narrow tube. It's a clever trick that basically magnifies the change, making even a 1-degree shift in temperature really easy to see. Of course, not all thermometers are built the same. Their performance really comes down to 3 key things. First is sensitivity. That's just how much the liquid actually moves for a small change in temperature. A super-sensitive thermometer is like having a high-resolution screen. It shows you all the little details. Then there's range. This one's easy. What's the coldest and the hottest it can measure before, the liquid freezes or boils? And finally, and this one is absolutely crucial for accuracy, is linearity. This just means that the liquid has to expand by the exact same amount for every single degree of temperature change. It has to be perfectly even or your whole scale is off. So if you're an engineer, how do you make a thermometer more sensitive? Well, we already saw one trick. Use a really narrow tube to magnify the liquid's movement. You can also make the glass wall of the bulb thinner. so heat gets to the liquid faster. And here's a cool one. Using a smaller bulb actually makes it more responsive, simply because there's less liquid that needs to heat up or cool down. But what happens when you need to measure something ridiculously hot, like the inside of a furnace? Or what if you need to measure a temperature that's changing super, super fast? A delicate glass thermometer with mercury or alcohol in it just isn't going to cut it. For jobs like that, we have to go back to that other physical property we mentioned earlier, electricity. This thing is called a thermocouple, and it works on a totally different principle. At its heart, it's just two different kinds of metal wire that are twisted or welded together at one end. And here's the magic part. When you heat up that junction where the two metals meet, it actually generates a tiny electrical voltage. The hotter it gets, the higher the voltage. So by simply measuring that voltage, you can figure out the temperature with amazing precision. So which one's better? Well, that's the wrong question. It really just depends on what you're trying to do. The liquid and glass thermometer is fantastic for sensitivity to small changes, but its range is pretty limited. A thermocouple, on the other hand, might not be quite as sensitive to tiny fluctuations, but it is an absolute workhorse. Its temperature range is massive and it's incredibly responsive. It reacts almost instantly. It's like you'd use one to check for a fever, and you'd use the other to measure the temperature inside a jet engine. And that really brings us to the big takeaway here. When you think about it, we can't actually see temperature. It's an invisible property. But the thing is, we don't need to. By being clever and understanding how temperature predictably affects things we can see, like an expanding liquid or a tiny voltage in a wire, we can measure that invisible force with stunning accuracy. You know, this whole principle, measuring the invisible by watching its visible effects, it's a real cornerstone of all science. And it kind of makes you wonder, doesn't it? What other invisible forces are we measuring every single day, just by observing the mark they leave on the world around us? Things like air pressure, or maybe even gravity itself.